So for this next learning module, we'll look at another example of static coplanar force systems, which is just a fancy way to say solving equilibrium problems in two dimensions. So in this particular example, we're told to determine the stretch in each spring for equilibrium of the 2 kilogram block. And we're also told that these dimensions which were provided correspond to the springs being in the equilibrium position. So it's kind of like someone was supporting this block up to a moment in time. They moved their hands away. And at that point in time when they moved their hands, they took a snapshot. And these springs haven't necessarily stretched yet. Because recall, as we kind of go over to our dot cam, that our spring law for an ideal spring states that the restoring force that's exerted by a spring is proportional to its displacement, where this proportionality constant is known as the spring constant. And it's just a measure of stiffness and tells us for a given unit of displacement, so notice that it's measured in newtons per meter, for a given newton of displacement, how much restoring force is exerted by the spring. So just imagine that you have this block or this cube or something, and we're told its mass, so from that we can determine its weight. And in this scenario, someone wanted to support it, but for some reason they couldn't make a direct vertical connection to the ceiling. They were forced to connect to these 2 points of connection at C and D. So the way that they kind of overcame these geometrical constraints in their environment is to use an O-ring and connect 2 different springs, one going up to B and one coming up to C. And these 2 together will provide a vertical force that counterbalances the weight, which corresponds, as we'll see in a minute, to the tension in the spring. And they'll kind of offset the horizontal force exerted on the O-ring by each other. So the pull to the right on the O-ring by this spring will be counterbalanced by the pull to the left on the O-ring by this spring. So let's actually solve what we're trying to solve here for. So again, we want stretches in springs, but we know that if we find the force exerted by a spring, which corresponds to the tension in the spring or its tensile force, we can always go back and get the displacements or the stretches as long as we know the spring constants, which we do. So basically our analysis here is going to try to identify some body that we could free such that when we actually make the segmentation and take it out of the real world into our free body diagram model, the forces of interest are isolated. So in this case, we want the forces exerted by each of these 3 springs. So naturally, the O-ring is a natural body by which to segment for our free body diagram. So if I do that over here, here's my O-ring, and it naturally has some dimensions to it. And here's the force that the spring connected from A to B exerts on the O-ring. Here's the force that the spring connected from A to C exerts on the O-ring. And here's that last force that the spring connected from the O-ring to this hook, which is connected to the load, exerts. So I'll just call this FAD. Now, naturally, this O-ring has some dimensions to it, right? It's a fabricated real structure. So it might not be immediately obvious that we can model this as a particle. However, if we extend the line of actions of each of these forces, we'll note that all of their lines of actions pass through a point which is dead in the center of that O-ring. So we called those concurrent forces. And we said whenever forces were concurrent, that a particle model was a valid form of analysis. So I'm actually going to go down here and redraw a free body diagram where I'm modeling the O-ring just as a dot. So it's not much difference because beforehand it was no, and now it's a dot. But I'm technically not showing kind of those segmented portions of the spring here that I would in a real free body diagram. So in the free body diagram, I want to be sure, since in two-dimensional or coplanar equilibrium, I only have 2 equations. So I can only determine 2 degrees of freedom or 2 unknowns. So I want to say everything that I can about the forces that are acting upon this particle. And forces are vectors. So namely, we need to, if we can, describe both the magnitude and direction. So you'll notice here that we're not given actual angles that describe how this force would be resolved into horizontal and vertical components for either this spring or this spring. However, we're given some geometry of a similar triangle that will allow us to do that decomposition. So I'm going to draw in the force exerted by this spring on the O-ring. And if you notice, in terms of its geometry, it's going to be at slightly less than a 45-degree angle because it's going to be similar to a triangle. If you kind of sketch this in here in your drawing, this side length is 4, this side length is 3. So it's going to be a little bit more in the horizontal direction than it is in the vertical direction. So I will draw that in there, and I will call that FAB. And I will know that geometrically, I can resolve this into xy components by solving for a triangle, which has a base length here of 4, a base length here of 3, and I could solve for the hypotenuse there by taking the square root of 3 squared plus 4 squared, which is going to be root of 9 plus 16, or root 25, or just 5. So that's how they're getting this 5 for the hypotenuse in a 3, 4, 5 triangle. For FAC, notice that its decomposition of the force triangle is similar to a triangle which has side lengths of 3 and 3. So it's just going to be up there at a 45-degree angle. So I'm going to draw it a little bit steeper. And at this point, I'm not going to overly worry about the lengths of these vectors because those are the unknown quantities that I need to solve for. Now, rather than carry this additional factor of 3 around, in my decomposition here, since a 3, 3, what would that be? Square root of 18 triangle is similar to a 1, 1 root 2 triangle. I'll just use these simpler side lengths in order to do my decomposition there. In the last force, which I need to show acting upon my particle, is the force exerted by the spring connected from A to D. And the one thing that I will say about this is, and we'll kind of see this technique in more detail later, if I kind of draw an entire decomposition of the box, which has a mass, so from that we can compute its weight, and we notice that this hook is actually serving to pull the box up. So that's the force exerted by the hook. And with respect to the spring, right, I could draw the hook in there, but for now I'll just assume there's no hook and it was directly connected to this point of connection in the box. By Newton's third law, if the spring pulls the box up, then the box pulls the spring down. And we know if the entire system is in equilibrium, then the box is in equilibrium. What that means is that we know the spring is pulling up by the weight. By Newton's third law, we know if the spring is pulling the box up by the weight, the box is pulling the spring down by the weight as well. We know that in order for the spring to be in equilibrium, that the O-ring up here is pulling the spring up by the weight, and in a similar fashion, that the spring is pulling the O-ring down by the weight. So what this shows is that the spring is in tension, and we know that the tension in that spring is equivalent to the weight of the box. And moreover, what really matters to us, because this is our particle of interest in our free body diagram, is we can say unequivocally that the force that's exerted by the spring connected from A to D is simply minus W J hat. So we know its direction because we know in general we model weight as being perfectly in the negative Y or J hat direction, and we know that the magnitude is W. So that might not be immediately obvious, but that's why that turns out to be. So now that we have our free body diagram and we've incorporated as much information as we can, if you notice we have the direction information for FAB and FAC, we know everything for FAD. So we only have two unknowns, magnitude of FAC, magnitude of FAB, and we can solve that by enforcing our equilibrium condition. Equilibrium says that the resultant force acting upon this particle is 0, and what that means is that the sum of all forces in the horizontal direction with the rightward direction denoted as positive must equal 0, and the sum of all forces in the vertical direction with the upward direction denoted as positive must equal 0 as well. So physically, what would this equation look like? Well, it's just going to say that the pull to the right by FAB is counterbalanced by the pull to the left of FAC. So let's decompose FAB into x and y components. In order to decompose it into x components, I would take the cosine of this angle here. Notice that by similar triangles, the cosine of this angle is equal to the adjacent side length divided by the hypotenuse of the similar triangle. So this is just going to be FAB times 4/5. And that is hard to read. I'm still getting used to writing on this. I've moved the doc cam to my office at SAC, and it's a little bit of a pain. So why is that going to the right? Well, that's our sign convention. Now, what about the pull to the left of FAC? Well, by a similar notion, that will be cosine of this angle, which is just going to be 1 over root 2. So that's going to be FAC times 1 over square root of 2. And that's going to be equal to 0. So I'm going to kind of hide that out since I took too much room to draw. But these are my coefficients, and these are my unknowns. And I'll rewrite this in standardized form below. What about in the y direction? Well, physically what I know is the pull up by FAB and FAC counterbalances in equilibrium the pull down of FAD, which is just the weight. So what that means is that the y component of FAB, which I can get by taking the magnitude of FAB, which I don't know, times the sine of this angle, which is just 3/5. So FAB times 3/5, that's positive because by convention it's pulling up. And FAC, which is just going to be 1 over root 2 again, 45-degree angle, so not surprising the x and y component are the same. Notice that the y component of FAC is up versus the x component was negative because it was left. And in the downward direction, we're going to have minus w, and that will be equal to 0. So let's actually write these in standardized form. And what that means is that we're going to write coefficient unknown equals constant. So writing kind of FAB as our first variable, the first equation is going to be 4/5 FAB minus 1 over root 2 FAC equals 0. And the second equation will be 3/5 FAB plus 1 over root 2 FAC. My high school algebra teacher would be mad at me for keeping a radical in the denominator, but that's okay because we're just going to put it in the calculator anyways. And the second equation will have a term on the right side, which is equal to w. Now this is your standard two linear equations and two unknowns, which in generally can be solved as long as the first equation isn't a multiple of the second or vice versa, as long as these are linearly independent. But I know you know how to solve these through various methods. You could solve them through substitution, you could solve them by elimination, but I'm going to show you, just to add a little bit of value to you, how you can write these in matrix vector form and actually solve them using a software package like MATLAB or your graphing calculator that may have matrix vector capabilities. So I'm going to take the coefficients of the two equations. I'm going to write the coefficient of the coefficients of the first equation in the first row. Now this only works if they're aligned in general form, meaning I have common variables underneath. So those are the coefficients of my first equation. Be careful with the sign. Coefficients of my second equation. I have my unknown vector here, FAB, FAC, that's what I want to solve for. And it's going to be equal to the constant term, which is going to be 0 and whatever the weight is. But rather than carrying the variable, the weight around, I'm just going to actually compute what that weight is. We know the mass is 2, and in order to determine the weight, we're just going to multiply by the acceleration due to gravity, which, as we discussed in chapter 1, we're modeling as a constant here on Earth. So it will be 2 times 9.81, and I have to be careful. This is in kilograms. This is in meters per second squared. So this will be in newtons. So let's actually compute what that is. Sorry. So 2 times 9.81, that will be 19.62. So this is the system of equations that you have to solve. So oftentimes in matrix vector form of linear systems, you'll call this matrix A. This is called the coefficient matrix. And you'll call this vector maybe the constant vector or the forcing vector. And we're going to be able to solve for FAB by taking the ratio of two determinants. The bottom, the denominator of this formula will just be the determinant of the coefficient matrix, and the numerator will be the determinant of an augmented matrix where I've manipulated that matrix in order to solve for, I'll write FAB. So you'll see what that means here in a minute. And this is a formula called Cramer's rule. So this will be FAC. The denominator is going to stay the same, but rather than augment the coefficient matrix in order to solve for FAB, I'll augment it to solve for FAC in the second case. So let me just show you what one of these looks like, and then we'll actually put it into the calculator. In order to determine FAB, what I want to do is take the determinant, which I usually denote by kind of absolute value signs around the matrix of that augmented matrix in the numerator, and then the denominator, I just have the standard matrix A. So I will rewrite that first. 4/5, 3/5, minus 1 over root 2, and 1 over root 2. So that's just the original matrix A. And what I do in order to augment to solve for the first unknown is I will take the second column and leave it the same, but the first column I will replace by the constant vector. And hopefully you recall from where you've seen the basics of matrices before, that when you take a determinant, you just multiply the product of the downward diagonal minus the product of the upward diagonal. So here in the numerator, it'll be 0 times 1 over the square root of 2 minus product of the upward diagonal is going to be 19.62 times negative 1 over root 2. And in the denominator here, it will just be 4/5 times 1 over root 2 minus 3/5 times minus 1 over root 2. So you can compute what that is in a calculator and solve for it, but I assume that many of you are just going to put this into your calculator anyway. So let me show you how to enter a matrix into MATLAB if you wanted. The way that you can enter a matrix into MATLAB is to enter row elements separated by commas, and I should say within a row, separate each element by a comma, and to go to a new row, enter a semicolon. So this is how you would enter the first row of the coefficient matrix. 5/5 minus 1 over square root of 2. And we will enter the second row, which is 3/5. And then the second entry is 1 over square root of 2. You can kind of put this in and echo to the command line and see that you're getting what you want. 4/5 is just 0.8, 3/5 is 0.6, 1 over the square root of 2 is about 0.707. So I'm going to call this F, I'll just call, what do I do? FAB, which is that augmented matrix that I need the determinant of. So I'm just going to take and copy my entry for A. But if you recall, going back to our dot can, we're going to make the first column 0 and 19.62. So this will be 0, and this will be 19.62. So that looks good. And the way that you determine a determinant in MATLAB is to use the function DET. So I'll say DAT of A FAB divided by DAT of A, and we will get the quantity here, 14.0143, which to 3 sig figs will just be 14.0 newtons. Now, technically, our final answer, we're looking for stretch or displacement, so I'm going to keep all of the precision in my answer that I've written here. So in order to solve for FAC, we're going to keep that same determinant on the bottom. So I'm just going to put determinant of A. But when we augment the coefficient matrix on top, rather than swapping out the first row, we'll swap out the second row with the constant vector. So that's the determinant that we need to compute now. So let's go back to MATLAB. That should be in newtons, I should say. And let's define a new, not FAB, but A FAC. And let's go back to the original A. Now, if you've used MATLAB before, you know there's an easier way to do this by just swapping out the particular column with one of the columns of A, but we'll actually hard code it in here. So now we're going to take out not the first column, but the second column. So we will make this 0, and we will make this 19.62. And we can look at the matrix and make sure it's what we want. And then we will say that in order to get our next quantity, we'll take the determinant of that augmented matrix divided by the determinant of A, and we will get 15.8554 newtons. Again, I'm not rounding yet because we're not to the actual final step. So the final step is, now that I know each of those forces, we'll actually determine what the book is calling the stretch, but really it's the displacement of each of those springs from equilibrium. So let's start with FAC, or let's start with a spring connected between points A and C. Remember that if that spring is in tension by this amount, then I can compute the displacement, which will be along the direction of the spring. So delta x here doesn't mean in the horizontal direction. This just means along the direction of the spring, as long as I know the spring constant. So we have an expression for FAC. So let's find the displacement by just taking FAC and divided by K in this case. So 15.8554 newtons divided by, and this is KAC, our particular spring constant, which is 20 newtons per meter. So if we compute that quantity, and I'm not going to round it, I'll use that answer exactly. If I divide that by 20, I get an answer of 0.7928 meters, which in engineering notation we would write as, let me go back to my .cam just to show you. So engineering notation, we always want the coefficient between 1 and 1,000. So to make this between 1 and 1,000, I can shift the decimal by 3 places, which will be 792.8. Recall, I just can't make a number 3 orders of magnitude bigger. So in order to do that, I have to add my 10 to the negative third adjustment. So this to 3 sig figs will be 793 millimeters in engineering notation. And you can do a similar thing, and I won't show you. Actually, I will. Why not? For the spring FAD, so we know that, let's actually do FAB first, since that was the other one that was obvious that we computed. We determine FAB, the force, to be 14.0143 newtons, and we know that the displacement of that spring will be FAB divided by whatever KAB is, so it will be 14.0143 newtons divided by that spring constant is 30 newtons per meter. So let's just do that really quick. Going over to here, 14.0143 divided by 30. If you convert that to engineering notation, you're going to get 467 millimeters. And then finally, the last one that we need to compute is the actual stretch of the spring that's directly attached to the weight. So that would be FAD, which we know to be W, which was just 19.62 newtons. So the displacement of that spring is going to be 19.62 divided by the spring constant of that spring, which was 40 in this case. So it was a stiffer spring. And that will be 19.62 divided by 40, 491 millimeters. It's been a long day. That's why this is exciting me, the rounding. I'm pumped around. Anyways, those are your 3 displacements. So the displacements were determined for a given spring stiffness by how much displacement you would see for a given force. And we determined the force in each case by just enforcing equilibrium on the particle model. And we could use a particle model because all the forces were concurrent at the middle of that O connector, which you can't see. I'm pointing it to it on the dot cam, but that's why we could use a particle model. So hopefully this all made sense. In general, you don't take this long to show the analysis, but I wanted to show you kind of a very, very detailed example of how this type of problem works. And I hope it was helpful.